stator voltage control. Okay, so now today's class we will see variable frequency speed control. In the sense we will vary the frequency, and by varying the frequency, uh, we will vary the speed of the induction motor. Okay, that is the objective here. So then we must to know first thing, what is the relationship between frequency and the speed. See here, uh, yeah, frequency and the speed, in the sense we have seen last class that what we have seen in the last class, uh, that by varying by stator voltage by varying stator voltage, we have seen that the speed and torque of induction motor are varied. This we have seen last class. Okay, so now we will vary the frequency now, stator frequency. The frequency, in the sense what, for the induction motor you give the supply to the stator. So that frequency is the stator. Okay, so that is the rotor, that is the stator. So you have the three-phase supply here, and also you have some frequencies there. So voltage and frequency is there. So by varying the frequency, you can control the speed of the induction motor. This is the logic behind. So for that some you require some equations. Okay, between the frequency and some other things. So for that, first we will see that voltage is proportional to flux, multiplication of flux, and you recall some EMF equation, EMF induced in AC coil. You have the AC supply. Okay, you have the AC supply, that is sinusoidal varying supply is there, and you give that to the winding. So transformer action is there. So means any winding, because your stator is also having winding and you are giving AC supply. So when you are giving AC supply to the stator, what is the EMF induced? That EMF induced are the voltage. Okay, so if you neglect the losses, EMF induced and the voltage both are same. So that is proportional to the product of flux and frequency. I hope you know this equation. Okay, so and what is the proportionality constant? You have 4.44. Then you have the number of turns are there. Then you have some winding factor, distribution factor. I hope you remember all these things in case of the stator windings construction. Okay, so that's the remaining all things you keep it as constant. So flux and frequency I can put like this. Okay, then from this what I can say is that, see this now. Okay, so then I can write this thing from this equation, that flux is proportional to V by F. This I can say. So what you need to understand here is that this equation we can get directly. Okay, so whereas if you see here, what you need to understand here is that, for example, now you know very well that this flux which is there, so here you are varying the frequency. So when you vary the frequency, the flux will vary, but generally you try to maintain this flux constant. Okay, so you have to maintain this flux constant. For example, from this equation, you decrease the frequency. Say for example, if you decrease the frequency, then what will happen from this equation? If you decrease the frequency, your flux will increase. But this you don't like. This you don't want actually. You don't desire this. You don't want to increase the frequency. You don't want to increase the flux. Why it is so? See here, from this equation, if you decrease the frequency, it shows very clear, because the voltage, what is this voltage now? The voltage you are getting from this source directly. So that voltage is constant. Okay, generally that voltage is constant unless you have some converter. In general, the supply voltage is constant. So if the supply voltage is constant and you decrease the frequency, why do you decrease the frequency here? I'll just show you here that one more equation which is related to the speed and frequency. I hope you know the synchronous speed ns is equal to 120 f by p. I hope you know this thing. Okay, so now you see there is a relationship between frequency and speed. Of course, of course. I will tell you one more thing. If you vary the frequency, your ns also varies. What is this ns? Ns is the synchronous speed, or you can say that it is the speed of the rotating magnetic field in the air gap. Okay, so you know very well the rotor always follows the rotating magnetic field. So rotor follows the rotating magnetic field. So if your ns is varying with respect to the frequency, you can vary the rotor speed also from the same equation. That varying frequency, your synchronous speed also varies. Then based on the construction, based on the principle, you know very well that the rotor always follows the synchronous speed. So if the synchronous speed changes, your rotor speed also supposed to be changed. So there is a relationship between speed and frequency. That's what I'm saying. Okay. From this simple equation, we can say that by varying the frequency, you can vary the speed also. But one problem we face, that problem we are discussing actually. What is that problem is that before we go to that problem, we know this thing, this equation very well, that V proportional to phi into F. From this phi proportional to V by F. Now here varying the frequency in the sense, let me take one case. What is the case? I decrease the frequency. When I decrease the frequency, what is supposed to happen? The flux will increase. But the increasing flux is not a correct one. Why it is not correct one is that if you try to increase the frequency, you recall this BH graph. Okay. The BH graph is there. Generally, now in normal conditions, you will operate the frequency somewhere here. You will operate the flux somewhere here, not a low value, because you know if you operate at lower value, the other parts is totally unused. So you don't want to be happen that. So generally, you operate the flux near to this part, near to this tip you operate. You generally in all the machines, okay, you generally have the frequency, you generally have the flux near to the end, you will have. So if you decrease the frequency, what is supposed to happen? Flux should increase. In the sense, this flux will move towards this direction. So it means it may enter into saturation. So this you will avoid. You don't want the core get saturated, because if the magnetic core gets saturated, then you have several disadvantages are there. It may enter into non-linear part, or it may enter into harmonics will inject. Okay, and the graphs become non-linear. All these problems will be there when the flux enters into the saturation part. So when the flux will enter into saturation part, when you increase the flux, when the flux will be increased, when you decrease the frequency. So when you decrease the frequency, so it should be very cautious that when you decrease the frequency, there is a very possibility that the magnetic core may be driven into saturation. That is, the flux will increase. This is the problem. So how to avoid this problem is that when you decrease the frequency, what you do is that proportionally you decrease the voltage also. See here, when you decrease the frequency, proportionally you can decrease the voltage also. So if you decrease the voltage and the frequency proportionally, now decreasing frequency definitely will decrease the speed here, because you see this equation. Okay, but other thing, what is the side effect is the side effect in the sense, what is the side effect here? Flux is increased. So when the flux is increased, this magnetic core will be driven into saturation. So that you don't want. Okay, then to avoid this magnetic core to enter into saturation, what you do is that you decrease the frequency, simultaneously you decrease the voltage also. So if you decrease the voltage and frequency proportionally, then this flux remains constant. Okay, so the core will not enter into saturation. That is the logic here. Why you decrease the voltage also. So when you decrease the frequency, you decrease the voltage also. So when you decrease the frequency, automatically speed decreases, but at the same time, the core will not enter into saturation. So here, first case is that decreasing the frequency. So when you want to do like this, what you should take care is that your voltage also should get decreased proportionally. Okay, so your voltage also should get proportionally. This is important. Okay, and then okay, this is called V by F control. Okay, this control you have to follow. So how can you decrease the voltage? Then you need a converter in between here. Once again, you need a converter here. So what this converter does is that this converter. So how do you implement this? That's the question. To decrease this converter, what it has to do? It has to change both voltage and frequency. So you need a converter here which can change both voltage and frequency. So this point you should keep in your mind. So you need a converter here which can change both voltage and frequency. So only that kind of things only will change both voltage and frequency. So you make the converter in such a way that you can decrease the voltage and also you can decrease the frequency. So now you see second case I will tell you. Now let me increase the frequency. So if you increase the frequency, what is the problem you will face? I will tell you. See here, there is a direct relationship between frequency and speed. That we know. Changing the frequency, speed also change. That we know. But the thing is that you have to be cautious. When you change, what are the other side effects also there? So that also you should take care. Otherwise, then you will face some other problems with this method. Okay. So one problem that when you decrease the frequency, your flux will be increased and it will go into the saturation. So to avoid this, proportionally you decrease the voltage also. Proportionally you decrease the voltage. Okay. For example, you increase the frequency. Second possibility is that you increase the frequency. So if you increase the frequency, speed will increase. This you know very well from this equation. But what is the other problem you will face? What is the other problem is that, see if you increase the frequency and assume that proportionally you increase the voltage, because the same method you are following in the first case, assume that you are following the same method in the second case also. But what is the problem? You have another problem. If you increase the voltage more and more, what is the problem is that there is a problem of insulation. Insulation breakdown. Insulation breakdown may occur. Why it is so? Because say for example you design the transformer for the rated voltage. You design the transformer for the rated voltage. Based upon the voltage only you provide the insulation and the windings. Okay, based upon the voltage only you provide the insulation. Okay, so now you see. So this voltage will increase. So just I'm discussing about the design of this induction motor. So you generally design the induction motor based upon the rated voltage. So based upon the rated voltage only you provide the insulation. So the insulation in the induction motor, it is based upon the rated voltage only. Now, when you increase the frequency here, and if you follow this V by F control, V by F control in the sense, this V by F you make it as constant. In the sense, frequency increase, voltage also increase. Frequency decrease, voltage also decrease. That's called V by F control. So first case, what is the first case? You decrease the frequency. That case you are following this method. For example, if you want to follow the same method here also, V by F control only, then if you increase the frequency, voltage also should increase. But what is the problem if you increase the voltage? The insulation which you have provided in the induction motor for the rated voltage is not sufficient. So if it is not sufficient, then insulation breakdown will occur. So to avoid this, what you do here is that you will not follow this method here. That is V by F control you will not follow. Rather, what you do is that when you increase the frequency at those times, you make the voltage constant. Okay. So you make the voltage constant. So this is what you do. See here, I will just repeat this frequency control, that the frequency and speed has a relationship from this equation. Okay. So then what does that mean? Either you can increase the frequency or you can decrease the frequency. First case, you decrease the frequency. When you decrease the frequency, as we have this equation, another equation which is there, which is affecting here. In that equation, what it shows is that when you decrease the frequency and if you maintain the voltage constant, obviously the flux will increase. But if the flux increase, then the magnetic core of the induction motor will enter into saturation. So if it enter into saturation, then there are so many lot of problems are there. So we don't want that. So in that case, what we do is that whenever you decrease the frequency, you decrease the voltage also proportionally. Then you maintain the flux constant. Okay, so you have to decrease the frequency, simultaneously you have to decrease the voltage. So now second case is when you are increasing the frequency. When you are increasing the frequency, if you follow the same method of V by F control, then you have to increase the voltage. But if you increase the voltage, what is the problem you will face is that there is a very possibility of insulation breakdown. So insulation breakdown in the sense, why insulation breakdown will occur? Because you design the induction motor only for the rated voltage. So when you design the induction motor for the rated voltage, then If you go beyond the rated voltage, that is voltage is increased here if you follow V by F control, then what is supposed to happen is that insulation breakdown will occur. So to avoid this, once again what you do here is that you will not follow V by F control here in the second case. Rather what you do is that when you are increasing the frequency and you came to know that the voltage is reaching to the rated voltage, then you maintain the voltage constant. So if you maintain the voltage constant, you see the flux is proportional to V by F. Okay, you increase the frequency here and you maintain the voltage constant. It is constant. Then what will happen to your flux? Flux will decrease. Okay, flux will decrease. So there is no problem with that. Up to some flux value, there is no nothing problem with that. But if you follow V by F control here, insulation breakdown will occur. So what is the conclusion here in both the cases is that when you are decreasing the frequency, at that time you follow V by F control. That is, you decrease the voltage also. But when you are increasing the frequency, it's better you maintain the voltage constant. So these are the precautions you will take while you are using the frequency control. Frequency control method when you are using, you better take these precautions in both the cases. Okay. So now the same thing. Okay. So now you see here. Now you see here. What you will understand here is that we will draw the torque speed characteristics. We will draw the torque speed characteristics. We will draw the torque speed characteristics here. This is torque. This is speed. This is torque. This is speed. Okay. So we see now. Okay. So this is F1, F2, F3. Okay. So here F1 greater than F2 greater than F3. Okay. So now you see, assume that you have a graph here. F1 graph is there. Now you decrease the frequency. So which case? First case. You are decreasing the frequency. So when you decrease the frequency, what will happen here is that when you decrease the frequency, so now when you decrease the frequency, so now the reactance is there, X is there, so it is 2 pi FL. I hope you know this thing. So when you decrease the frequency, your reactance will decrease because it is proportional to the frequency. So when the reactance decreases, it means impedance decreases, Z decreases. If Z decreases, it means I increases. Okay. If I increases, then the torque is proportional to I. This you know very well. Okay. So I cannot say directly proportional or it is so, but definitely I will say this thing that torque is proportional to power and power is proportional to V into I. So in other words, I can say this thing that it is proportional to I. So if I decrease the frequency, that is F1 to F2, let me decrease the frequency. So it is decreasing like this. So when I decrease the frequency, you will find out yourself is that your reactance decreases because reactance is proportional to F. So impedance decreases. If impedance decreases, your current will increase. If the current will increase, torque will increase. So that's the reason that you will find out here that your maximum torque has come here at this speed. The maximum torque has come at this speed. But when you decrease the frequency, the maximum torque will come at lower speeds. This is lower speed. See, the speed is increasing in this direction. In the sense what? This is zero speed. Now you are increasing. So first case you got at some higher speed, but when you go on decrease, you will find out the maximum torque has come at lower speeds. So this is This is what I can say. In another words, also we can explain this thing. Okay. So in slip also you can take, because speed you can turn as slip here. Okay. So you can take here zero slip. You can take here as slip one. Slip one. So slip one is here. Slip zero is here. So this time the slip increase in this direction. Okay. So this is the relationship between torque and speed by different frequencies. Okay. Now the same explanation which I have given here, I will explain using the block diagram. One block diagram I will draw now. So using that diagram, we will just explain. Okay. So, so how do you implement this? That's the question now. We have seen this that for decreasing frequency you follow one method, for increasing frequency you follow another method. Okay. So how do you implement that? I told you that one thing, to implement this we need a converter here. So that converter is that VFVS is the converter. What is VFVS is that variable variable frequency variable frequency variable voltage source. So this box which I have drawn here, it is a variable frequency variable voltage source. Okay. So that's a converter. That's a converter. So that converter will give variable voltages and variable frequencies. So now from that converter you just go to the induction motor. So you have the induction motor here. Stator of the induction motor is there. So actual supply is here. I told you just now that between source and induction motor, you need a converter. I told you that converter is this one. What is that converter? Variable frequency variable voltage source converter. This is the converter. So now, but what is the input to this converter? Because you have to follow one important thing in this. What is the thing you have to follow is that, so you here marks in there. Now this blocks you call it as flex control. Okay. So what this represents, I will tell you that what these blocks combinedly does is that, okay. So just now I told you one important thing. That thing will implement these blocks. Okay. I told you already that this part, which one? This part of the block diagram, it implements the just now I have shown you that when the frequency decreases, when you want to decrease the frequency, what you have to do, when you want to increase the frequency, what you have to do, that I told you. So that logic or that algorithm will be implemented by these two blocks. Okay. I will show you the graph here so that you will easily understand. It is voltage, it is frequency. Okay. So you see the graph, it's important. So this point, what is this point? This point, it is base frequency, or you can call it as rated frequency. Okay, this base frequency. So if you see here, the frequency is 0 here. So till base frequency, the relationship between voltage and frequency is proportional. The relationship between voltage and frequency is proportional. Proportional in the sense, you increase the frequency, voltage also increased. till this point. But after that you see it has reached rated voltage. It has reached rated voltage. After that, even though you increase the frequency, means after this point, I will take this point as A. So till A, the relationship between voltage and frequency is proportional. So you increase the frequency, voltage also increased till rated voltage. That is till rated voltage. This one, that is V by F control. I will say 0 to A. It is V by F control. V by F control in the sense both have proportionality. You decrease frequency, voltage also frequency decrease. If you increase the frequency, voltage also increase. That till A. But beyond that, if you want to increase the frequency, you cannot increase the voltage. Rather, you maintain the voltage constant. That's the reason you put the horizontal line. So this part is constant voltage. This I have shown you just now, that while the for low while you decrease the frequency, you decrease the voltage also. But when you want to increase the frequency, if you want to increase the voltage, it go beyond the rated value, so insulation problem will occur. So to avoid this, we are taking this method. What is that method? 0 to A. For below base frequency, it's a proportionality, but above the base frequency, you maintain the voltage constant. Because otherwise, insulation problem will occur. So this graph will be implemented by this block, the block which I put in the black color, and as per that only you will get the command to your converter, and based upon that, converter will give the output voltage. So converter will get a command that if it is below base frequency, then if the frequency decreases, voltage also decreases. This is what it does. But if the frequency is above the base frequency, then the command will come that you maintain the voltage constant. So that's the purpose of this block diagram. Okay, so now you see. So then I would like to solve a simple numerical problem. A simple numerical problem will solve at first. Okay, so I will just note down the question first. The three base connected induction motor as the parameter. Ohm, R2 dash is 0.35 ohm, X1 0.95, 0.95 ohm, X2 dash is 1.43 ohm, and Xm is equal to 28 ohm. And then the speed of the motor is controlled by varying stator voltage and frequency. The voltage to frequency ratio at the rated condition is kept constant. Determine maximum torque and speed at which it occurs for data frequencies 50 Hz, 35 Hz, and 10 Hz. Okay, so this is a question now. Please see the question. A three-phase 1460 RPM, 415 volt, 50 Hz, 4-pole star connected induction motor has the following parameters. Okay, so he has given the data as a three-phase induction motor. Okay, then the speed of the motor is controlled by varying the stator and frequency, stator voltage and frequency. The voltage to frequency ratio at the rated condition is kept constant. It means V by F is kept constant till the rated voltage. That is till the base frequency. Rated voltage or base frequency. So, and then determine the maximum torque and speed at which it occurs. So you have to find out the maximum torque and also what is the speed at which the maximum torque occurs for the stator frequencies. So three frequencies he has given. So for every frequency we have to solve the problem. First we will take 50 Hz. We will take for 50 Hz. So what you have to find out maximum torque and the speed at which it occurs. So you have the formula for the maximum torque. I hope we have an equation for the maximum torque. Already we might have got that in the previous class itself. We got that. So I will write down the equation here. The maximum torque equation. T phase square whole divided by 2 minus R1 plus square root of R1 square plus x1 plus x2 dash whole square. Okay, I think this is the equation. Okay. Now you see what we don't know in this. First is V phase. What is V phase? Go to the data. What is the data? That the voltage is 450 volts, but it is three phase and it is star connected. So in star to star, you know the line voltage, and what is the phase voltage? 415 by root 3. That is the phase voltage. Next, what you need to know here, omega s. So omega is in a sense, what is omega s? Omega is the angular frequency. So it is angular frequency. So how do you find out the angular frequency here? So 2 pi n by 60. Now if the speed he has given, okay, how do you find the speed here? Yeah, we have to find out ourselves. Okay, because the data he has given first case is 50 Hz. Then if it is 50 Hz, yeah, omega is synchronous speed. What is the synchronous speed for 50 Hz? 120 f by 2. Okay, then you get 120 into 50 by number of poles are 4 he has given. 1500 RPM. So this is 1500 RPM. Then what is omega s from this? 1500 by 60. So what we get here is that 157 radians per second. See, I'm directly writing the answer here. Just do that, you will get the answer. So we got omega. Then R1 value also he has given. We show you the R1 he has given in the problem as 0.65 ohm. X1 0.95 ohm. Then X2 dash 1.43 ohm. So everything he has given in the data. Then directly we can substitute in the equation. Everything is a known value here. Then you will get the answer. See, I directly substitute that. Please, I will get the answer directly here. 174.5 96 Newton meter. This is the maximum torque. Now you recall yourself. There is a formula you might have got. The slip at which the maximum torque occurs. There is a formula. Okay, SM. The slip at which the maximum torque occurs. What is that formula? Is that R2 dash? See, all this you might have got in the induction motor. Otherwise, you just reverse R1 square plus x1 plus x2 dash whole square. So then you will get everything here. Everything 0.R2 he has given 0.35. Everything he has given here in the problem. So substitute in this. So then you will get the answer 0.142. So this we got the slip 0.142. But we don't want the slip, rather we want the speed he is asking. So what is the relationship between speed and slip now? See, ns minus nr by slip is equal to ns minus nr by ns. Then what is nr from this? Ns you take common 1 minus s. That's it. So ns value is 1500 into 1 minus s is 0.142. That's it. So if it is 0.142, then you got the answer approximately 1287 rpm. So we got the answer. So we got the answer for 50 Hz. Now what is the answer for 35 Hz? One is 35. Same procedure you follow. 35 Hz in the sense, what is the difference you will find out? Unless there is a difference. 120 f by t. So 120 into 35 by dt is 4. So what we will get here is that we should here 120 into 35 by 4. So we will get 1050 rpm. So once we got 1050 rpm, then what is from this we can find out omega s also. We can find out omega s also. So what is the omega s you will get here? Omega s is 2 pi n by 60. That is omega s. So what you will get here from this? This now 1050 into pi into 2 divided by 60. Yeah, you got 109.95. 109.96. This is omega s. Then what is required? Because we are just checking the formula. In the formula, whatever you require. So VPH it is constant. There is no change in that. Okay. Whereas omega s we have find out. Then R1 there is no changing. R1 is, but X1 X2 there are changes. Why X1 X2 are changing? A simple answer. Why X1 X2 are changing? Because X1 X2 they are frequency. Only for the X1 X2 when the frequency is changing. Here X is proportional to F. So if X is proportional to F, now the X which he has, for example, X1 he has given, how much is 0.95. So X1 he has given, that is equal to 0.95 ohm. And remember, it is for 50 Hz. It is for 50 Hz. That 0.95 he has given. But now you have to find out X1 for 35 Hz. How do you find out that? Simple, 0.95 into 35 divided by 50, because it is directly proportional. Then what is the answer we will get here? The answer we will get is 0.665. 0.665. So likewise x2 dash also you can find out. x2 dash for 35 Hz. Because in the data he has given the 50 Hz. You have to find out for 35 Hz. Okay? So 1.43. So 1.43 into 35 by 50. How much will get is 1.001 ohm. And remember, okay, these are the values of X, but R1 R2 will not change. Why? R1 R2 they don't depend on the frequency. So what are the frequency? Omega s. And now second one is X1, Only these three will change. The remaining formula remains same. The remaining formula, whichever I said, it remains same. Okay. So then what you do once again, you take these two formulae once again, substitute them, you write the x and you remain all the previous values. Then you will get for T max and the slip for the maximum target. You can do the same procedure even for the frequency and head also. Then you will get the answers. Okay. So the remaining two things, partially the second thing and the complete third part, I'm just giving to you. Okay. So you can solve that. Just substituting in the equations, you will get the answers. No problem. Then we will go to another simple topic. So we'll discuss about voltage source inverter. So I am sure that voltage source inverters you already got in the electronics. So, I don't want to tell more about this, but rather what I would like to tell here is that I will do one thing for the time available. So voltage source inverter. See, voltage source inverters which we have seen last class are in the polytonic course. Okay, I don't know. See whether it is whether so now either you can make these inverters using the thyristors, or you can make using the transistor also, the BJT. Either you can use this or you can use this. Okay, there is no problem because the ultimate requirement here is that what is the ultimate requirement? The ultimate requirement what we do here is that we need a AC supply. That is what we require here. Okay, otherwise nothing else is there. So we need AC. So how this work? I will just tell you. Using the thyroid transistors, I will tell you next class, but using thyristors, I will teach you now. It takes hardly 5 to 10 minutes, not more than that. Okay, first I will draw using the thyristors. I hope you know that, but let me draw the circuit diagram first, then I will start explaining. I hope you know the. I will take single phase inverter. I will take single phase bridge inverter. So first you have single phase bridge inverter. First you will have 4 thyristors, and every thyristor is associated with a diode. It requires for the conduction, for the freewheeling conduction. The diodes are required for the freewheeling conduction. So single phase bridge you will have 4 switches. I hope you know this thing. Every now I'm taking it as a thyristor. So every thyristor has an anti-parallel diode for the freewheeling action. Here, now here you have the load. So this is the main circuit. The load here is the induction motor. Anything, any load which requires AC supply. Okay. Now I will get the DC supply here. I will get the DC supply somewhere here. Now this DC supply. Okay. This is the DC supply. Here you have. So now you see now. As these are thyristors, so total how many thyristors are there? I will give the number in here. 1, 2, 3, 4. You know very well this thing that thyristor. So now here, what is the inverter actually it works? See here, this is the source VDC. You turn on 1 4 at a time, so that the output voltage, the current will flow in one direction. That is in the flow, and it makes a closed box. Like I will show you here. It goes through your thyristor 1, then to the load, then to the thyristor 4, and after that It makes the closing part. Okay. So this is one closed path. Now the other case is, so in that case the direction of the current is like this. So you have, so the output is positive plus. The output is positive plus, something like this. Positive. Okay. Now I turn off 1 and 4 and I will turn on 3 and 2. So when I turn on 3 and 2, what is the direction of the current in that case? We will find out. The direction of the current will be, take another color here, something like this. So then to the type 3, then comes to the load, then to then to the thyristor 2, then it makes the reverse. So this blue color one, you see red color one. Now if you see in case of the load, you see the red color one is flowing from left side to right side, whereas the blue color lines are flowing from right side to left side. In the sense, when you turn on 3 and 4, it will get reversed in the load. Okay, so it gets reversed in the sense you get something like this. You will get negative. That's it. So you know very well in very single phase project. Now, what is before you turn on 3 and 2, you have to turn off 1 and 4. You have to turn off 1 and 4. You cannot turn on 3 and 2. Then you need a computation circuit here. You need a computation circuit here. So computation circuit for what? Computation circuit for turning off 1 and 4. For turning off 1 and 4, computation circuit we require. So that one I will draw now. The computation circuit I will draw now. Okay, now this is the power circuit. So this is the operation. Everyone knows this thing, simple operation. Okay, but now you require a computation circuit also. So that is a little bit thing you need to understand here. So I will draw the computation circuit now. So right here, 1A. Okay. This is the resistor. We'll give a name here R1. There is another diode, and there is another thyristor. This is 2A. This is 2A, and then that's it. Then you have an inductor, and you have a capacitor. You have a capacitor, and this capacitor is connected at this point. Now you see now. So this 1A, 2A thyristors and their diodes. It is for turning off 1 and 2. Remember, it is for turning off 1 and 2. You can take like this. Whereas for the remaining two thyristors, 3 and also another commutation circuit. So that commutation circuit I will draw this side. Okay. So okay, this is R2, P2, L2. Okay. It is 3A, it is 4A. Then I let me join this entire thing. Yeah, I would like to explain one commutation circuit. Remaining 3 switches you can understand yourself, no problem. Okay, so see this. Okay, so commutation circuit, let me start. So now assume that 1 and 4 are conducting. 1 and 4 are conducting. So you want to turn off 1 and 4. You want to turn off 1 and 4. Then, so that let it turn on 3. That is your turn off. So to turn on 3 to first you have to turn off 1 and 4. Now first I will take 1. How to turn off 1 is that to turn off 1, To turn off one, I will turn on 1A. I will turn on 1A. Oh, yeah. I will turn on 1A. Why I am turning on 1A? It's very important. I am turning on 1A so that the thyristor 1 will be turned off. So when I turn on the thyristor 1 is turned off, I will show you now. So before this happens, actually there was a voltage across the capacitor in the. Now you will get this. So you will get the next half cycle, not now. You will understand this. How come this negative here plus here? You will understand the next half cycle. But for the time being, you believe me that when 1 and 4 are conducting, then at the time the capacitor voltage here is minus and plus polarity like this. And I turn on 1A. When I turn on 1A, what do you expect when I turn on 1A? That this DC voltage is there, which is there here. It will flow through 1A. Then after that it comes here. After that it travel through this inductor L1, C1. Okay. So L1, C1. Okay. And what else? L1, C1. Then you see here L1, C1. Then after that, after C1, it comes to this junction. Then it will take the path which is to the diode. You can make like this. So see RLs you see here. You want to make through the diode. You see here, this is turned on. So when this is turned on, oh, not I'm sorry. Uh, okay, now I will just start over once again. I'm sorry for that. So there is a mistake here. What is the mistake? I will you know. So 1 is conducting, 4 is conducting. So what I'm going to do is that to turn off 1, I will turn on 1A. So when I turn on 1A, what is exactly happens is that this capacitor immediately starts discharging. This is what is happening here now. When I turn on 1A, this capacitor starts. Now show you how it discharges. Charging like this, then it will enter into this diode 1, then after that it will take this path, then it will go like this, then after that it comes like this, then it enters to 1A. For 1A, then it enters into the inductor, then capacitor. So it makes a closed path. So it makes a closed path like this. Yes. Now you see yourself in this closed path. In this closed path, you see yourself. What is the thing you will find out is that this capacitor has some voltage with this polarity, some VC I will take. VC I will take. Then what you find out is that this we have the partial voltage VC here. Then it makes a closed path like this. Then please find out what is the voltage across this thyristor now. Apply KVL in this. So if you apply KVL in this, then immediately this voltage VC, okay, will be applied across this thyristor VC. So it means there is a negative voltage applied across thyristor 1. So once a negative voltage is applied across thyristor 1, it means you are turning off thyristor 1. So how do you turn off the thyristor 1 here? So here logic I will just repeat once again that the procedure is that 1 and 4 are conducting for the positive half cycle. Now 2 and 3 we have to conduct for the negative half cycle. But to turn on 2 and 3, first you have to turn off 1 4. Otherwise a dead short will occur and this dead short will kill all the device. So to avoid this, what we do is that you turn off 1 and 4 first. So first I want to turn off 1. How I am turning off 1 is that I have a commutation circuit. In this commutation circuit, I turn on 1A. When I turn on 1A, by that time what the voltage with this polarity minus and plus, it takes it through D1 and thyristor 1A and L1 and C1. So it makes a closed path through C1. Here is D1, then it is 1A, then L1. So when it is making a closed path through the diode D, what happens exactly is that you see yourself now here. Okay, what is the kind of voltage will be applied across this thyristor? Okay, what is the kind of voltage will be applied this thyristor? So as the diode is conducting, you can take that the diode voltage will be applied across this. So there is a negative voltage appears across this, and that negative voltage will definitely turn off the thyristor 1. Okay, so this is This is how the thyristor 1 is turned on. Similarly, what happens is that 2A is also like that, 3A, and whichever you want to turn on. For example, you want to turn off 4, then you turn on 4A. You turn on 4A. This you turn on 4A. Similarly you want to turn off VA. Sorry, similarly you want to turn off. So whichever, every thyristor has a alternate. Every thyristor has a alternate thyristor. For 1 there is a 1A is there. For 2 there is a 2A is there. For 3 there is a 3A. For 4 there is a 4A is there. So you want to turn off 4, then you turn on 4A. That's it. That's the logic you follow. You want to turn off 3, you turn on 3A. Okay. Okay. For example, you turn on 1A, then you turn on 4A, then automatically 1 4 will be 1 4 will be definitely 1 4 will be off, and then you turn on 3 and 2. When you turn on 3 and 2, what exactly happens is that okay, what exactly happens when you turn on 3 and 2? Then the negative half cycle will come. So negative half cycle will come. So once the negative half cycle will come, then the cycle repeats. Now here you may get a question here is that when do I turn off 1A? What should I do to turn off 1A? So to turn off 1A, what you do exactly is that see here, now the current is flowing in this direction. Now it is a LC circuit. See, in this closed loop, what are the components you have? Please see L1, C1, then D1, then 1A thyristor. See, D1, 1A, these two are thyristors. So they are just like short circuit. Then what is left in the short circuit? LC is left in the closed path. So when LC circuit, it means something like this. L is there, C is there, then so LC circuit is there. So this is minus, this is plus, take an assumption. Then the current is flowing like this. When the current is flowing like this, it is flowing like this. What happens when it is flowing like this? See yours. When it is flowing like this, what will happen now? The capacitor will charge in the opposite polarity. You might have seen all these things in the power electronics, I'm sure about that. So the capacitor flows, the current in the capacitor flows in this direction. When it is flowing in this direction, after some time, because of this LC circuit, if you recall this resistor, then you turn on your side, the capacitor polarity will reverse like this. This becomes minus, this becomes plus. Yes, it happens like this. That is the nature of the LC circuit. So now the new polarity, the new positive of the capacitor is here, the new negative of the capacitor is here. So here also same thing. The new positive will be here, new negative will be here. That's it. So when this happens, then now you turn on. So for example, one complete cycle is over. Now you enter into the second cycle. So when you enter into the second cycle, what you do once again? You turn on 1 and 4. So it means you turn on 1. So when you turn on 1, what do you expect now? When you turn on 1, okay, this 1 is turned on. Then what do you expect now? See, the new positive of the capacitor is this here. The new negative is this here. So then what happens when you turn on 1? When you turn on 1, what exactly happens is that this plus is here, whereas this minus is here. In the sense, here is your minus, here is, so 1A will be turned off. That's what I'm saying. So I can say this thing that 1 and 1A are complementary thyristors. See, this is the commutation circuit I'm explaining, not the power circuit. Power circuit is already over. Power circuit is very simple, that you turn on 1 4, you get the positive half cycle. You turn on 2 3, you will get the negative half cycle. That's the power. That's the power circuit. But here, what I'm discussing is that what is the commutation circuit. When you want to go to 3 to turn on, how do you turn off 1 4? That is the point we are discussing. So to turn off 1, you turn on 1A. That's what I'm saying. Similarly, to turn off 1A, you turn on 1. That is the simple thing to understand. So it means what we can say, 1A are complementary thyristors. Similarly, 2A are complementary thyristors. 3A are complementary thyristors. 4A are complementary. So complementary thyristors in the sense, you want to turn off one thyristor, then in that pair you have another thyristor is there, so you turn on that thyristor. For example, 1A, they make a complementary pair. So you want to turn off 1A, you turn on 1. Similarly, you want to turn off 1, then you turn on 1A. So this is called complementary. Okay, so this is how the single phase bridge inverter. Okay, this is single phase bridge inverter which I have explained using the thyristors. Okay, now using BJT, you have another circuit is also there.